Awesome. Well, thank you very much. And I guess, you know, since I'm the last speaker, I think I'm supposed to like lead a round of applause for the organizers for this. So, you know, that's, I can't hear you, but I'm assuming there's applause going on. You know, I wish, unfortunately, like, I'm sorry I cannot be there in person. I would much rather be in France than in South Bend, but, you know, it's just the way the timing works. So I'm going to talk about the Steinberg representation. So this is going to be sort of an unusual talk. You know, I'm a topologist, and I'm giving a talk about representation theory to an audience of number theorists. So I hope that I will be able to convince you that this is relevant to all of our lives. Anyway, so I'm going to start. Oops, I have to push a button so I can do this. Okay, I'm going to start from the beginning. So let's see. Oh, and don't, I will never actually notice the chat. So interrupt me just by talking if you want to talk. So we can talk about the Tits building. Oops, let's see. So let K be a field. So for instance, just think about Q or a finite field. So the Tits building is a simplicial complex. It's the R simplices of the simplicial complex are flags of length R+1 inside K to the n. So we don't allow, you know, so 0 and K to the n are not allowed, but all the intermediate pieces are, those are the vertices, and they, you know, they form simplices if they fit together in a flag. Those are they're subspaces of K to the n. So the maximal flags, the maximal simplices have n-1 terms, but we start off with 0, so therefore this is an n-2 dimensional simplicial complex. So let me give you some examples just so we can learn to think about it in simple cases. So Tits 2 of K, well, this is flags in K squared. And so there, you know, all there are lines inside K squared, but there's no inclusion relations. There's no instance relations. And so therefore, this is just the discrete set of lines in K squared, or which is also called just P1, but not with the Zariski topology, just like literally with the discrete topology. So it's just a set of points, the set of lines inside K squared. Tits 3 of K, this is actually a bipartite graph. So there's two kinds of vertices. So the zero simplices are proper non-zero subspaces of K cubed, and there's two kinds. There's lines and planes, and I've illustrated them in blue and red. And there's an edge between a line and a plane if one is contained inside the other. Okay, so this is as I said, it's a bipartite graph, and I want to make an observation that it's a connected bipartite graph. So it's enough to show that I can connect any two distinct planes by some path, right? Because every line is contained inside a plane. So if I can connect any two planes, then I've shown you that this graph is connected, and that's not so bad. I have a linked two paths. So it starts off at the plane P1, and then it goes to the line P1 intersect P2. So you see P1 and P2 are both two-dimensional subspaces of K cubed, and so they intersect in a line. They're distinct ones. I chose that. And so therefore you just have a path from P1 to P1 intersect P2, and then back up to P2. So this is not just a connected, it's a connected graph, it's a connected bipartite graph, but it's a very narrow graph, right? Like it's not like it's very small diameter. It only has diameter 2. So it's sort of squashed in there. But it is, if K is an infinite field, this is still an infinite graph. So it's very sort of packed. It's got a lot of vertices, but they're sort of packed in very tightly amongst each other. Okay, so that's the Tits building. So what can I say about the topology of this building? Well, there's a remarkable theorem of Solomon-Tits that says that Tits n of K is homotopy equivalent to a wedge of n-2 dimensional spheres. Remember from the previous slide, the dimension of the Tits building is n-2. And so therefore this says it's a wedge of spheres of the top dimension that could be inside there. Let's think about some special cases. So Tits 2 is a discrete set. Remember, it's just the discrete set of lines inside K squared. And a discrete set is you know, that's for, you might not think of it like this, but it is. It's a wedge of zero-dimensional spheres. Remember, a zero-dimensional sphere is just 2 points. We wedge them together just by sticking the base points there. So just as long as you have a discrete set that's got more than 1 point, it's a wedge of S naught. So I guess if it's just got 1 point, it's a wedge of 0 copies of S naught. It's still a base point. Anyway, so this is a discrete set. Tits 3 of K, we just argued in the previous slide, was a connected graph. A connected graph is a wedge of circles. This is a familiar fact to topologists. All you do is, so you have some kind of complicated connected graph, you choose a maximal tree inside that graph. You can always do that. So it's a subtree, so it's a connected tree, it's got no cycles, and it contains every vertex. You can just sort of construct that. You just start adding vertices to this one at a time while keeping it a tree. And if you keep going, eventually, maybe using Zorn's limit, if it's infinite, this will be a maximal tree. And a maximal tree is contractible. So you squash that maximal tree to a point, then suddenly all the vertices are identified. This doesn't change the topology because you're contracting a contractible thing. And you're left with a single vertex and a whole bunch of edges coming off it. So that's a wedge of circles. Anyway, so these special cases are, they illustrate the Solomon-Tits theorem. And this says that this kind of pattern persists for higher n. Okay, so now I want to make an observation. So why did I introduce the Tits building? Well, I introduced the Tits building. This is encoding the sort of combinatorics of linear algebra, right? And so the main player in linear algebra is the general linear group. So GLNK acts on the Tits building because GLNK acts on the vector space k to the n by linear maps. And that preserves, preserves subspaces. It takes a line to a line, a plane to a plane, and so on. And it also preserves instance relations. And so therefore, the Tits building is, I think of it as the sort of combinatorial sort of superstructure of linear algebra. And so the general linear group acts on that. And therefore, the general linear group acts on the homology of the Tits building, just by functoriality. And so there's only one interesting non-zero homology group because the Tits building, you see it's a wedge of n minus 2-dimensional spheres. And so the only interesting homology is in degree n minus 2. And well, that's the Steinberg representation. So the Steinberg representation of GLN K, and I'm going to put coefficients in C just for simplicity. This is, by the way, can people see my my mouse right here when I move it?
Yes.
Okay, good, because I'm going to use that to gesture. So the Steinberg representation, which I'm going to note as SDN of K, this is the homology in degree n minus 2 of the Tits building with complex coefficients. And I'm going to put reduced homology just because that's the right thing to do for various reasons. So it's the reduced homology. It's the only non-zero reduced homology group of the Tits building. And so it's a representation. So it's a vector space, a complex vector space on which the general linear group acts linearly. Okay, so this is going to be the main player of the talk, the unique non-zero homology group. And I know it's a lot of definitions. If you don't think about this very often, what you're going to see later on in the talk when we start actually proving things, I'm going to do a little bit of, I'm going to prove the simplest special case of my theorem. I'm only going to focus on Tits 2. And so therefore, this homology group is really just going to be H0. So there's nothing fancy that's going to be going on, at least topologically, in that part of the talk. Okay, so I have this Steinberg representation. It's somehow, it is the vector space that's encoding the structure of linear algebra. Okay, so I move the definition up to the top of the slide so we can have it here. So what do we know about this? Well, this was first studied for not for infinite fields, but for finite fields. It's a basic fact. The Steinberg representation is finite dimensional if and only if K is a finite field, like F2 or F3 or so on. In that case, it was studied by Steinberg in the 50s. Steinberg in 1951 proved that for any finite field STN of FQ, so the Steinberg representation of GLNFQ is an irreducible representation of GLNFQ. Irreducible, just to remind you, this is a representation V of a group G, so that's a vector space in which the group G is acting linearly. It's irreducible if it has no interesting subrepresentations. The only subrepresentations are 0 and V. Okay, and so Steinberg proved this for the Steinberg representation. Let me make some remarks about this. So if you haven't thought about the representation theory of groups like GL and FQ, you sort of know, you might think that it's not so hard to come up with interesting representations. Because GL and FQ, it was born into this world to act on vector spaces, namely to act on FQ to the n. So GL and FQ acts on FQ to the n. It acts on tensor powers of that and wedge and exterior powers and symmetric powers and so on. But those are all representations in the defining characteristic. It's not so easy to find interesting representations that are complex vector spaces, even though we know from basic representation theory that there are a load of irreducible complex representations of the Steinberg of the general linear group. And so the Steinberg representation is the sort of most important of all those different representations. It plays a basic role in the representation theory of these finite groups of Lie type. And I should say, just because it'll come up later on, so I'm talking about the Steinberg representation of GLN, but there's other Steinberg representations. There's Steinberg representations of any connected reductive group. The flags and K to the n, well, the stabilizer of a flag is a parabolic subgroup, and so the simplices of the Steinberg representation of a general reductive group are just the parabolic subgroups. And more generally, I think Curtis was the one that finally gave the most general version of this. For any connected reductive group over a finite field, the Steinberg representation will give you an irreducible representation of it. Anyway, so this is an important piece of the representation theory of finite fields, but I'm interested in infinite fields. And so why should I want to explain to you why I care about this and why you should care about this. So why should number theorists care about the Steinberg representation? So the basic fact is a theorem of Borel and Serre. So Borel and Serre proved that the symmetric space Xn for SLNZ has a bordification. So the symmetric space, this is the sort of basic contractible space which a group like SLNZ acts. It's in this case it's SLNR modulo a maximal compact subgroup modulo SON. So this is a non-compact symmetric space. It's encoding flat metrics on tori. And it had, but so because it's a non-compact space, we are driven to want to construct a boundary to it. We want to figure out what's going on in infinity. And Borel and Serre proved that it has a bordification. So it's the interior of a manifold, and the boundary is homotopy equivalent to the Tits building. Okay, so let's see here. I'm not sure if you can. I can't actually see the word Tits in that right there, so I'll move that so I can see it at least. So it has this this bordification. So in other words, another way of saying this is so this symmetric space is some non-compact manifold. This Xn hat is a manifold with boundary. So it has the same algebraic topology as Xn, but now it's a manifold with boundary. The boundary is homotopy equivalent to the Tits building, and the quotient by SLNZ is compact. Okay, so they constructed a co-compact bordification. And what this is saying is that if you look at the Steinberg representation over Q, Stn of Q, so this is the unique non-zero homology group of the Tits building over Q with complex coefficients. This is the homology at infinity for SLNZ. And because of this, it plays a basic role, for instance, in duality phenomenon for the cohomology of SLNZ and so on. There's a lot of work on doing computations, of various cohomology groups of SLNZ using this. And so it shows up all throughout the study of the cohomology of arithmetic groups like SLNZ. Let me give an example here so you can see if you haven't thought about this in a while or ever. So here's the easiest example of Borel-Serre's theorem. So the easiest example is when n equals 2. And so the symmetric space X2 for SLNZ, this is just the upper half plane, the set of complex numbers with positive imaginary part. So how does SL2Z act on the upper half plane? Well, a matrix ABCD like this, it acts by linear fractional transformations. So it takes a number Z inside the upper half plane to AZ plus B over CZ plus D. And that, if Z has positive imaginary part, so does AZ plus B over CZ plus D. That's something that I think is familiar to most of us. And here's a picture of that action right here. So there's sort of two matrices you might be interested in. One is the parabolic matrix 1, 1, 0, 1, and that corresponds to Z goes to Z plus 1. So that's just translation by one step to the right. Another matrix would be 1, 0, 1, 1, negative 1, and that's the that's one. Yeah, so that's the map that takes Z to negative 1 over Z. So that's it's like a rotation around this point I right there that preserves I, and it's sort of a rotation around I. And so we see this famous picture of the fundamental domain for the action of SL2Z on the symmetric space. We have this, here is the unit circle centered around 0. Here are the two lines with, this is negative 1/2 and this is 1/2 right there. And this region above here, every point in the upper half plane can be uniquely taken to a point in here, except on the boundary. There's some boundary identifications that are done. So Z goes to Z plus 1 takes this vertical line to this vertical line. So those two are glued together. And this rotation, negative Z goes to negative 1 over Z, it fixes that red point and it identifies this part with that part. And the quotient is the famous modular curve, so the most important object in number theory. So we see this red point and this purple point go to these two special points, and then we have this cusp. It's a sphere with a cusp heading out to infinity right there, and that is when you go vertically up. Z goes to Z plus 1, that's this cuspidal region right there, the point of non-compactness. And we can see that the quotient of H2 by SL2Z, the modular curve, is not compact. It looks like there wants to be something going off out here, right? You want to be able to when you can go off to infinity and you want to attach a boundary at infinity right there. And so that's what Borel and Serre do. And there's an easy picture of this. So how do we boardify this? So the goal is to attach a boundary, but in fact, it's not, this is from even just a point set topological point of view, this is not as easy as you would like. So Borel-Serre's paper is very technical because they know what the boundary is supposed to be. And so they know what the space is as a point set. But when you actually want to define the topology on the union of the symmetric space and this sort of points at infinity, it's pretty technical. But Grayson had a beautiful idea. He said, well, if we believe that this is the interior of a manifold boundary, we should be able to just chop off a Collar neighborhood of the boundary. And that what we do is, instead of finding the boundary outside and putting it on our space, we're going to find the boardified space inside our space just by chopping off a Collar neighborhood. And there's a beautiful picture of that for H2. And here it is. What we're going to do is we're going to cut out balls around the cusps of the modular curve to get the H2 hat, the boardification of H2. And so what we're going to do is, you see this famous packing of circles inside the upper half plane right here. We have a circle that's tangent to every rational number down here. And there's a single orbit of circles. These are horospheres under the action of SL2Z. For instance, Z goes to Z plus 1 takes the large circles, translates them one of the large circles. It takes these next smallest circles to those. And then, if you take Z goes to negative 1 over Z, that, it interchanges some of these things. And we can just keep iterating this process, and we get deeper and deeper into these smaller and smaller circles. So these circles, they get smaller and smaller, but they're all disjoint. And so the complement is supposed to be our boardification. So what we're thinking of is these horospheres, these horoballs, are a Collar neighborhood of infinity inside this manifold boundary. So if we remove them, we get something that is, well, homeomorphic to the space we're looking for. And so we have this space H2 hat. It's still contractible. We're removing all these balls. They're all disjoint. So it's still a contractible manifold boundary. That's not so hard to see. You can deformation retract the whole thing to this chopped out thing. You just sort of push out among these horospheres right here. You just have to push out to sort of squeeze out. And so we have this beautiful space. The group SL2Z acts co-compactly on here because we no longer can go off to infinity. We removed, for instance, this horosphere up here, the one that's tangent to the point at infinity. If we try to go off to infinity, we bump into this, and so we can't go. So SL2Z acts co-compactly on this space H2 hat. And what's the boundary of this space? Well, we see, when you first look at this, you think, well, the boundary is a whole bunch of circles, right? But these are not actually circles. The reason they're not circles is because they're missing the point where they're tangent at infinity. So these are circles, but they're missing the very bottom point where that lies on the line, the real axis, which, remember, the real axis does not lie inside the upper half space. And so therefore, in fact, the boundary components of this space H2 hat are a bunch of real lines. This is a real line right here. It goes around here. These are all little real lines. We can see one that really looks like a real line up here. So, and remember, H2 will take, not H2, SL2Z will take this horosphere centered in infinity to one of these. And so therefore, these really all, even though they look different to our sort of Euclidean eyes, hyperbolically, these are all the same thing. And so the boundary is a whole bunch of copies of the real line. It's sort of a complicated, like if you think about walking around here, this is sort of a complicated topological space, right? Like you can walk here and you have these walls that go off to infinity. You can follow the wall for a while, but then you move over here, you're following another wall. And so it's this sort of tree-like pattern of walls heading out to infinity. And so there's a copy of, there's a boundary component for each rational number plus infinity that corresponds. There's a boundary component for each point Q on the real axis where you have one of these circles tangent to it plus infinity. That's this up here. Okay, so now Q union infinity, that's also called P1, right? And so each of these boundary components is contractible because it's the real line. And so, oh, by the way, so why is Q union infinity P1? That's just slopes of lines, right? And so therefore the boundary is homotopy equivalent to the discrete set of lines inside K squared, given by the slope. And that's also called the Tits building. So we found this is how Borel-Serre's theorem works in the simplest possible case. Okay, so that is the boundary, the boardification. So that's why, because of the fact that it's the boardification, the boundary, the topology infinity, that's how I got interested in these Steinberg representations. And of course, the relevant Steinberg representation is in this case of GL well, GL in Q. So it's over an infinite group. So what about, those are the Steinberg representations we're going to care about in this talk. What about infinite fields? So if we were looking at an infinite field like Q, then the Steinberg representation is an infinite dimensional representation of the infinite group GL and K. Now, you got to be warned. So representation theorists talk about infinite dimensional representations all the time, but usually they want those representations to have some sort of additional structure. They want it to be continuous or algebraic or something. And this has no structure at all. This is just a naked infinite dimensional vector space acted upon by this sort of discrete infinite group. So it's not algebraic, continuous, or anything like that. And so therefore, the sort of the usual tools of representation theory just have real trouble dealing with this sort of situation. In representation theory, certainly when you first learn it, it feels like the goal of the subject is to quickly get away from vector spaces and start talking about things like characters or something like that. And so here you really have to confront the naked vector space. Let me tell you some previous results about this. So Zhai in 2014 proved that if the field is the algebraic closure of a finite field, ST in FQ bar, that this is an irreducible representation of GL and FQ bar. So that is, he proves this. So the algebraic closure of FQ is a union of finite fields. And so he sort of shows that this is sort of a union of the sort of finite Steinberg representations. And so he's able to, in a clever way, reduce himself to the case of finite groups where that was proven by Steinberg. But that's only going to work in this very special case. Galasius, Coopers, Randall Williams, much more recently in 2020, proved that in fact it's always an indecomposable representation. Remember that a representation V of a group G is indecomposable if you cannot write it as a direct sum U plus W for proper non-zero subrepresentations. And so for finite groups and representations over fields of characteristic zero, so you need both of those conditions. This is equivalent to being irreducibility, just because everything splits as a direct sum of irreducibles in that case. But in general, for infinite fields or for infinite groups or for representations of finite characteristic, this is a much weaker condition. But I do want to give you an observation about this. Galasius, Coopers, Randall Williams, those are three homotopy theorists. They're sort of geometric homotopy theorists, but they're homotopy theorists, and they cared about this Steinberg representation. Not for sort of number theoretic reasons or representation theoretic reasons. They cared about it because of its relationship to algebraic K theory. So this is one of those objects that sort of shows up all throughout mathematics, I think largely because reductive groups like GLN, they show up everywhere, right? So anywhere that linear algebra shows up, probably the Steinberg representation has some role to play. Okay, so my main theorem is, there's only one theorem I could give you if with this buildup. This is with Andrew Snowden. So for infinite fields K, the Steinberg representation is an irreducible representation of GL and K. Let me make some remarks. More generally, as I said, there's a Steinberg representation for any connected reductive group over a field, and our theorem has no hypotheses. It works for any connected reductive group over any infinite field. Now you should be warned. Oh, by the way, even the non-split one. So I grew up thinking of, I learned, when you learn the theory of reductive groups, you start off by learning the split ones like SLN or SP and various orthogonal groups and things like that. And I was sort of scared of the non-split case, but it's not as scary as I thought it was. I sort of learned the non-split case so we could keep generalizing it. So we started off by proving this theorem for GL2 and then for GLN, and then for some of the split ones, we did it a case at a time, and eventually we managed to keep generalizing it until we removed all the hypotheses from the theorem. Another remark. Oh, by the way, so we define the Steinberg representation, where this is the unique non-zero reduced homology group of the Tits building with complex coefficients. In our theorem, the complex coefficients can be replaced by any field, and the proof is basically uniform. It doesn't use anything about the field of definition, the field of coefficients, the C. If you replace C by any field, the same proof works. I should make a warning for you. So I said this is a theorem about infinite fields. This does not specialize, and that's a real hypothesis. So this does not specialize. If you took our proof, it doesn't give you a theorem for finite fields, because. And the reason for that is, as I said, like we can prove this for there's no hypothesis. You can replace C with anything. In particular, you can replace C with a different field, a finite field. And for finite fields K, there exist other fields F so that this non-zero homology group is reducible. So for representations, say, of GL and FQ, some of the Steinberg representations in certain characteristics are reducible. So therefore, something special has happened. For infinite fields, that phenomenon doesn't occur. But that's why our proof really uses the infiniteness of the field very carefully, very sort of fundamentally. And so my goal for the rest of the talk is I want to prove the simplest case of this. So I want to prove this. I'm going to impose two conditions here. I'm going to first just focus on GL2K because there's sort of two reasons for that. So for GL2, you see the Steinberg representation is H0. So you don't really need to know any topology to think about H0 of a space. It's so simple. It's a very simple and concrete thing. The other thing though is that you're going to see the sort of fundamental roles can be played by unipotent subgroups, and for GL2K, the relevant unipotent subgroups are all abelian, and so therefore you're going to see we're going to do some commutative algebra, and for higher n we'd have to do the proof uses non-commutative algebra. So this lets me take the sort of scary non-commutative algebra and replace it by simple commutative algebra. The other hypothesis I'm going to make is that the characteristic of K is going to be 0. So for instance, it could be Q. The proof is actually quite different if K has finite characteristic. If it's an infinite field of characteristic P, you actually have to do some number theory. You'll see. I'll explain where our proof goes wrong if you were trying to deal with finite fields. And I know it's an audience of number theorists, so I shouldn't say, well, I want to avoid all the number theory. But I couldn't really explain that part of the proof in a talk. It really wouldn't make sense. So I'm going to prove this special case. So that is what the remainder of the talk is about. So to first do that, I have to tell you something about the structure of the Steinberg representation, how the Solomon-Tits theorem works. So I'll keep trying to remind you of definitions as I go on. I don't expect you to have memorized all my previous slides. So define U2. This is the 2x2 strictly upper triangular matrices over the field K. So it just matrices look like this: 1, lambda, 0, 1, where lambda is some element of our field K. Okay, so this is a nice abelian group. And what I claim is that there is an isomorphism iota between the Steinberg representation and the group ring of this abelian groups, the complex group ring of U2. Now, what kind of isomorphism is this? This isn't just a vector space isomorphism. So the GLN acts on ST on the Steinberg representation, but there's not an obvious action, if GL2 does, is not an obvious action of GL2 on the group ring of this unitary group. So we're going to bring in the group action later on. But right now, I just want to construct a vector space isomorphism between these two things. Okay, and how can I do it? So remember, what is the Tits building? The Tits building is the discrete set P1. So it's just the set of lines inside K squared. And the Steinberg representation, this is reduced H0 of the set of lines inside K squared. And so what is reduced H0? Well, if this wasn't reduced homology, this would literally just be formal linear combinations of lines. That's what H0 of a discrete set is. It's just formal linear combinations of points in the discrete set. Because I'm taking reduced homology, it's formal sums Ci, Li, where Ci is a complex number and Li is a line, and the sum of the coefficients is 0. The sum of the coefficients is 0. That's because I'm working in reduced homology. And so, of course, the Steinberg this set of formal linear combinations has an obvious basis, right? So you just take, so I'm using homogeneous coordinates inside P1. So every line in P1 can be written as, this A comma B, where, if we scale them, we get the same line. This just corresponds to the line that goes to the point AB. And so a basis for the set of formal linear combinations where the sum of the coefficients is 0 is just, we take the line of slope infinity, the line 1, 0, minus some other line. So a line lambda comma 1. So 1, 0 is the line of slope infinity. All the other lines, we can scale the second coordinate to be 1. So all the other lines are uniquely of the form lambda comma 1 for some lambda inside K. And so this 1, 0 minus lambda 1 is a basis for the Steinberg representation. Just as a vector space, as a complex vector space. Now, I've written this, you sort of see what's happening. I see 1, 0 minus lambda 1, and you look at U2, we also see the column 1, 0 lambda 1. And that is going to be our isomorphism. So the basis element 1, 0 minus lambda 1 corresponds to the matrix 1, lambda 0, 1. And remember, in the group ring, we can take formal linear combinations of these matrices, right? And similarly, elements of the Steinberg representation are just linear combinations of these basis elements. And so these, I've matched up bases for these two vector spaces. And so that's going to be our isomorphism, our vector space isomorphism between them. Okay, so I want to move that to the top because I don't want to forget that definition for the moment. So I have this vector space isomorphism between the Steinberg module and the group ring. And so there's a question. So I want to make an observation. So GL2K acts on, well, it acts on the Steinberg representation. So because I have this isomorphism, I can transport that to a really weird action of GL2K on the group ring of this U2, of this unipotent group. It is really a strange action. It's hard to wrap your head around. So there's two parts, there's two bits of it that are pretty easy. So U2 is, of course, a subgroup of GL2K. And that part of the action is really simple. It's just the obvious action on the group ring by left multiplication. So that's not so bad. Another group that, oh, by the way, so I want to make an observation. What this says, and that you see, I told you I'm going to be doing some commutative algebra. So what this says is that subrepresentations of the Steinberg representation will correspond under this isomorphism to ideals inside the group ring. So my theorem will be like the real theorem that we prove will be about, I want to understand ideals inside this group ring. Okay, so it's going to reduce us to a theorem in commutative algebra. Now, the other part of GL2K that we can understand are the diagonal matrices. So diagonal matrices act by conjugation. So let's do a little exercise to see how that works. How does the diagonal matrix D1 act on this basis element 1, 0 minus lambda 1? Well, of course, it just scales this, so it takes 1, 0 to, well, D0 and lambda 1 to D lambda, 1. But we're working in homogeneous coordinates. So that's just 1, 0 minus D lambda, 1. So diagonal matrices permute these basis elements right there. Okay, so therefore, it really should correspond to some way of making these diagonal matrices act on the U2. And there's only one thing, there's conjugation. So let's just check this. You see, if you conjugate 1 lambda 0, 1 by the diagonal matrix D1, so we put D0, 0, 1 here and D0, 0, 1 inverse right here, of course, you do the little matrix calculation, you see that it also multiplies the upper right-hand coordinate by D. And so these are the only two pieces of the action that I really understand in a simple way. The action of the subgroup U2 of GL2K and the action of this algebraic torus, the diagonal matrices, they act by conjugation. Okay, so these are the only ones that I have to understand for most of the proof. But I am going to have to use the rest of the action somewhere, and you'll see that that's going to happen in the next slide. But I'm going to avoid doing the isomorph. I'm going to try to do all the computations inside the Steinberg module as much as possible. Okay, so now I understand this, and I have this first clue that there should be some connection between the subrepresentations of the Steinberg representation and ideals inside this group ring, the group ring of U2. Okay, but now the theorem, we're not done yet. And the reason we're not done is, of course, there are ideals inside the group ring, right? You know an ideal, there's the augmentation ideal. So there's an augmentation from the group ring to C. It just takes, a formal linear combination of matrices and takes you to the sum of the coefficients. Take the kernel of that. So that, and so we have to make sure that, that ideal right there does not go to a subrepresentation of ST2K. That's the thing we have. That's one thing we have to fight against. We have to fight against that non-zero ideal. Okay, the non-zero proper ideal. And so here's, I'm keeping this vector space isomorphism right there. So let epsilon from the group ring to C be the augmentation map. So it just sums the coefficients of the matrices. And so what I claim is that the augmentation ideal of the group ring does not correspond to a subrepresentation. What do I mean by that? So here's the claim. If you have any non-zero vector inside the Steinberg representation, then, well, it might go to the kernel of the augmentation map, but if I hit it with an appropriate element of GL2K, then it goes to something that's not inside the augmentation ideal. So if this claim were not true, then we would be in trouble. There would be, the pullback of the augmentation ideal would be a subrepresentation. So the theorem would not be true. So we have to prove this somehow. How do you do this? Well, okay, we have to go back to the definition of the Steinberg representation. Remember, the Steinberg representation is reduced to H0 of P1. So it's formal linear combinations of lines, and the sum of the coefficients is 0. By the way, this is a confusing point. There in this case, there's sort of two different augmentations going on here. There's the augmentation on the group ring, and there's the augmentation on non-reduced H0. These are two different augmentations. Do not confuse them. Anyway, so an element of the Steinberg representation is a formal linear combination of lines. It's non-zero, so at least so the coefficients are all non-zero. You might as well make the lines all distinct, and the sum of the coefficients is 0. Okay, and what I want to do is I want to hit this x with some element of GL2K to make sure that it goes to something on the right-hand side where the augmentation is non-zero. How am I going to do that? Well, what I'm going to do is I'm going to pick some element G inside GL2K that takes the first line to the line with slope infinity, so line 1, 0. I can do that. GL2KX transitively on the set of lines. And so now I said when I was writing X in this way that all the lines are distinct. So all the other lines do not have slope infinity. So they're lines of the form lambda I comma 1. They have slope lambda I for some finite lambda I for all the other coefficients, all the other terms. And so GX is the sum. Well, we take C0 times 1, 0, this line in infinity, because we hit this with X. The next one goes to C1 times lambda 1, 1, and all, et cetera, up to Cn lambda n comma 1. And now I need to use the fact that the sum of the CIs is 0. I can write this in terms, remember, this is my basis for Steinberg. It's differences between the line of slope infinity and the line and some line of positive slope, or not positive, non-zero slope. And so we see, because the sum of the coefficients is 0, I can rewrite this. Well, that means that I can rewrite this as negative C1, 1, 0 minus this. And so you see, when you expand this guy out, the negative sign right there and that negative sign cancel each other. So we're just left with C1 lambda 1, 1 up to Cn lambda n 1. Lambda n1, but then we're also left, but then the coefficient of 1, 0 is, well, it's negative C1 minus C2 up to minus Cn. Well, that's the same thing as C0 because the sum of the coefficients is 0. Okay, that's great. And what do I see then? I see that if I hit this, if I move this over, so each of these basis elements becomes a matrix inside U2. The augmentation of it just sums up these coefficients, negative C1 up to minus Cn, which is the same thing as C0, which is non-zero. Okay, so just by following my nose, by playing around with matrices, I was able to prove this claim. I proved that the augmentation ideal of U2 does not correspond to a subrepresentation. So my theorem is at least at this point not obviously false. So I keep looking at my watch to make sure I'm doing my timing correctly. Okay, so my theorem is not obviously false, but it's not yet it's not even close to true. But at this point, I'm going to be able to forget about the structure of the Steinberg representation and just focus on this group ring. So let me make an interlude from subrepresentations to ideals. So remember, my goal is to prove that the Steinberg representation is an irreducible GL2K representation. If V is a non-zero subrepresentation and I is iota of V inside the group ring, then what is I? Well, I already said it's an ideal. That's just because the action of U2 on the Steinberg representation, just as a subgroup of GL2K, is the same as the action of U2 on this group ring. So I is definitely an ideal. It's closed under conjugation by diagonal matrices. That's really going to be the key here. And it's also, by step 2, it's not in the kernel of the augmentation map. Okay, and now at this point, I'm just going to focus on ideals. So my goal theorem, I'm going to instead of thinking about the Steinberg representation, I'm going to think about ideals in this group ring. My goal theorem is that if I have an ideal that satisfies these conditions, so I have an ideal I inside the group ring that's closed under conjugation by diagonal matrices and not in the kernel of the augmentation ideal, it's got to be the whole thing. And this, I should say, like everything I've been doing up till now, this works in general. The same proof works. You just replace U2 by UN, and you have to use something about the structure of buildings. But if you go through the sort of structure of buildings argument you have to do, it just specializes to exactly what I'm doing. So, you know, I think when I first learned about buildings, they seemed hopelessly abstract. But if you take something about it and you specialize it to this most degenerate case, you really see it become something sort of simple and concrete. And this is an example of that. Okay, so now you can totally forget about the Steinberg representation. We're just going to focus on this goal theorem. And as I said, this is sort of a theorem in commutative algebra. It's about group rings of a billion groups. for higher end, you'd have to do something about group rings of non-abelian groups, and that becomes more complicated. Okay, so now we want to prove this, and we see these diagonal matrices have to play some important role here. And so we have an ideal that's not contained inside the augmentation ideal, but we have to use the diagonal matrices somehow. So that's step 2, is we're going to use the torus, which the diagonal matrices are an algebraic torus. So here's my goal theorem again. And so I know I is not inside the kernel of the augmentation map. So therefore I can find some x inside I, well, that's not inside the kernel of the augmentation map. So x is of the form, well, it's some linear combination of matrices where the sum of the c's is non-zero, and I can scale that so the sum of the c's is 1. Okay, so I can find some x inside the my mystery ideal where the sum of the coefficients is 1. Now, let's remember we have this calculation. So I is closed under conjugation by a diagonal matrices. And if you conjugate this matrix 1 lambda 0 1 by the diagonal matrix D1, it multiplies the lambda by D. Now this, by the way, I remember I told you I'm using the fact now that that we're working over a field of characteristic 0. Of course, if we're working over a field of finite characteristic, these diagonal matrices might not be invertible. So that's why things are much harder if we're working over fields of infinite fields of finite characteristic. You have to do something sort of more arithmetic in that case. But here we can just do this. And what does this mean? So what this means, so I have this x, this lies inside my ideal, right? Well, if I define xd to be just ci, and then I just multiply the upper right-hand corner by d, I know that that's also inside I for all d, right? All d at least 1. So I've now produced a large number of elements inside my ideal. Now, what do I really want to do? Well, I said this is true for d at least 1. What I really wish I could do was replace this d by 0. Now, of course, that's nonsense, right? Like, it's not an invertible matrix, so that wouldn't make sense. But if I could multiply lambda I by 0, then I would get the identity matrix. So that's what I want to do. I want to show that if I just define x0 to be just, ci times, and we put 0 up here, well, what is that? That's the sum of the ci's times the identity matrix. That is just the identity matrix because the sum of the ci's is 1. I scaled it to make that true. And if I knew that was inside I would be done, right? If I contains the identity matrix, that means it contains every other matrix, and therefore it's the whole thing. Okay, so I just want to, I have this huge supply of elements inside my ideal, and I want to show that I could just formally replace d by 0. So I have it for d is equal to 1, 2, 3, 4, 5, 6, 7, and I want to somehow go down by 1 to 0. Okay, and so this is, I just restated what I have. I have and this is all you need to know. I have an ideal. X sub d is just this guy right here. And I want to prove that x0 is inside I. And I know xd is inside I for d at least 1. Okay, so I want to now reduce this, as I said, to a theorem in commutative algebra. And so, the group ring of this thing is kind of complicated. I want to talk about just the easiest group ring I know, which is just, Laurent polynomials over the integers. And so I'm going to define a ring homomorphism from Laurent polynomials over the integers to this group ring, and zi is going to go to the matrix 1 lambda 0 1. I can do that. So there's a sort of universal property. This is sort of free, right? So I can just take the zi's to any units I want inside this group ring, and so these are the units I'm going to take them to. And so I can define a ring homomorphism like that. And what that means is that if I take zi to the d, well, what does that do? That takes it to, 1 d lambda I 0 1, right? So I have this ring homomorphism, and zi to the d goes to the things I want. And so I want to make an observation. So what does this do? So this turns the group ring into a module over this ring of Laurent polynomials, right? A left module. I guess it's commutative. We're in a commutative situation, so it's just a module. And it has a submodule I, right? And so, and I know that I have that if I take x sub d, that's zi to the d times this thing right here, I know that's inside I for all I. And I want to show that's also true for zi to the 0, right? And what I'm going to do is I'm going to remove all the content from this statement. I'm going to prove an abstract theorem in commutative algebra that is the most optimistic, crazy thing that could possibly be true and give you this result. Okay, and that's going to be on the next slide. As I said, I designed this talk to be sort of a process of forgetting. At every slide, you can forget sort of everything past like 2 slides ago and still follow it. So I'm going to show this, want to show this holds for d is equal to 0. And I'm going to prove just an abstract result. I'm going to prove something very general. And so what is that general statement? So here's the lemma. So let's let M be any module over this ring of Laurent polynomials, and let N be any submodule. Let little m1 through little mn be inside M, be elements of M such that zi the d mi is inside N for all d. And I want to prove that the sum of just the mi's is inside N. You see, this is exactly, if I could prove this, that would have given me what I wanted before, because I just replaced M by this group ring, right? And I replaced these M sub i's by, well, I'll do it right here. I replace these M sub i's by these guys, these CI's times the identity matrix. Okay, so if I could prove this lemma, which has, it feels like at this point I've taken away all the content. So like, it's, could this be true? But it's true. Okay, so let's prove this right here. So how am I going to do this? The first thing is I'm going to replace M by the quotient M mod N, so I can assume that N is 0. Okay, so now I know that the sum of the zi of the d times mi is equal to 0 for all d at least 1, and I want to show that the sum of the mi's is 0. Okay, now the next thing is there's no hypothesis here that M is finitely generated, but that's not a problem. I can replace M by the submodule generated by the little M sub i's, and then I can assume M is actually a finitely generated module. And that means once I'm dealing with finitely generated modules, then I can actually do commutative algebra. I can do like localization and stuff. Okay, so how am I going to prove this? I want to show that this guy, the sum of the M sub i's is 0. That's my goal. And to do that, well, consider a maximal ideal alpha inside this ring of Laurent polynomials. It's enough to show that if we localize at this maximal ideal, the sum of the mi's is 0. Remember, in commutative algebra, if you have some element and it's 0 when you localize it, every maximal ideal, it's got to be 0. So this is like if you have a vector bundle and you have a section of a vector bundle and it's 0 at every point, then it's actually the 0 section. Which so that is basically the same statement. Okay, so I have to show that this sum of the M sub i's is 0 in this localization. So how can I do that? Well, I'm going to use the Kroll intersection theorem. What does the Kroll intersection theorem say? This is equivalent to showing that the sum of the mi's is inside the intersection of the alpha of the r times m, as r goes from 1 to infinity, right? So the sum of the M sub i's lies inside alpha r to the m for all r. Then if that's true, then it's 0 inside the localization. That's, by the way, where I'm using the fact that M is finitely generated. I need that to use the Kroll intersection theorem. So let's fix some R. Now, I know that if I take my ring of Laurent polynomials and I mod out by alpha to the R, well, that's a finite ring, right? Because remember, if you have a maximal ideal inside this ring of Laurent polynomials and you intersect it with Z, you're going to get some non-zero ideal inside Z, right? Some non-zero proper ideal. And so that cuts us down to the situation where we're working over a finite field. And so this is a finite ring. This is a sort of a mystery finite ring. I don't know what the structure looks like, but I do know that it has units Z1 through Zn. Okay, so for a fixed R, if I mod out by alpha the R, I get a finite ring with these units. And because it's a finite ring, each of these units has finite order, right? So I can find, and then I can just take the GCD of the orders, and I can find some D at least 1 such that Zi of the D is equal to 1 mod alpha of the R for all I, right? So I can find some common exponent such that each of these units, you raise to the dth power, it becomes 1. That's great. So that means that 0 is equal to, well, remember, I know that the sum of the Zi to the D times mi is 0, right? So that's true. But now if we're working modulo alpha of the R, now each of these Zi to the D's become 1, right? So that becomes the sum of mi's, mod alpha to the R. So that means that sum of the mi's is equal to 0, mod alpha of the R. So therefore, the sum of the mi's is inside alpha of the R, which is what I wanted to prove. Okay, so as I said, this is it's sort of an abstract proof, and you might wonder how you would do this in the in the setting where maybe I was working over, in the non-commutative setting for higher n, we have to deal with these non-abelian unipotent groups, not unitary, sorry, unipotent groups. And there you have to use, there's this remarkable deep work of Philip Hall on the module theory, modules over group rings of nilpotent groups, of finitely generated nilpotent groups that you have to use. And that's sort of the replacement for the Kroll intersection theorem. So that's the it's worked for the 50s, but it's one of these things, it's the kind of thing that geometric group theorists have used. They use it to prove things like residual finiteness, so that certain groups inject in their pro-finite completions. But though there's been a huge amount of work in infinite group theory since the 50s, I think the proof of Philip Hall's theorem has never been simplified. It's still a remarkably complicated theorem. So that's the real thing you used to make this argument work for higher n, at least over fields of characteristic zero. So okay, I think I'll stop here. Thank you very much for listening.
Okay, let's thank Andy for his talk. Again, we don't hear anything, but I'm sure.
Really, you don't hear anything. I'm very surprised.
Now we hear you. Now we hear you.
I can hear you talking. Yeah. So
there were really strong applause.
Okay, that's good to hear.
Do we have any questions for Andy?
So I do have one, but I'm just asking first the people. Comments, questions?
So it's just about the D.
Okay.
So here in the definition like that diagonal matrices. So here D is always just a natural integer.
Right.
Okay.
That's right. Yeah. D is always just a positive natural integer. That's right.
Yeah, but when we say the diagonal matrices, so the diagonal matrices they don't necessarily restrict to matrices with integer coefficients, right?
Well, I want to remind you, we're working, the entries of our matrix are lie in a field of characteristic 0, right? Yes. And so therefore they all contain Q, and therefore it makes sense to plug a natural integer into them.
Yes. Yeah, but can we have other coefficients? That's my question.
Oh, you're asking about fields of finite characteristic. Yes, the theorem works for fields of finite characteristic, but you can't, this proof doesn't work, obviously, because those D might become 0, right? If we're working over a field of finite characteristic. And the proof there is quite different. You have to, the beginning stages are the same, but the sort of ring theory part is quite different. You have to do something arithmetic. In the end, you use the Chevalier-Varning theorem. You use the fact that you can solve, systems of polynomials, polynomial equations over fields, over finite fields. If you have you can always find non-zero solutions if you have enough variables. And so we're working over infinite fields of finite characteristic, and so you can make the number of you can use that to sort of as a trick to sort of make the number of variables you need to solve you can imagine there's lots of identities you need to be true to make this kind of argument work. And you can make sure that there's enough space to find them all like that. But it's quite a different argument. It has a very different flavor.
Okay, thank you very much. And also, it's still in this direction. And so for example, in theory, we could have used a D, for example, a rational number at first.
Right.
In the matrix, in the matrix action. But why we cannot hope that this would work for D0? Because that we don't have additional structures, right? Because, for example, for me, if we have continuity, this kind of structure, we could hope that we can extend this to D equal 0. But
that's right.
Like an important remark that there's no additional structure that we cannot make this argument work.
That's absolutely correct. Yeah, and that's one of the things that makes these representations hard to work with. There's no continuity whatsoever. Like you have to deal with them as somehow just naked vector spaces. They're really, so you can't you can't take limits of things. That just doesn't make sense in this context.
Thank you very much.
Yeah, so in fact, my question is related to the last question. What can we say more if we assume that the field K has a natural topology?
Right. So there is, so if the field is a like a local field, then there is a like a smooth Steinberg representation. You know, that shows that's the kind of thing that shows up in the you know, the representation theory of p-adic groups and stuff like that. And that is quite, that is also irreducible. I don't remember who proved that, but that has quite a different flavor from this. The smooth Steinberg representation. What you do to define it is there's, and I don't, who did this? I like, there's papers of like Sayre that did this a long time ago, but I don't remember who did this first. But there's a way of retopologizing the building that takes into account the topology of the field, and then the non-zero homology group gives you what you want. So it's a, but as I said, like that's irreducible, and that shows up, that's sort of shows up in, like, as I said, like the representation theory of p-adic groups and stuff like that. But it's really has a completely different flavor from this one.
Okay. Those are questions in the room?
Are there no more questions?
No more question in the room.
Okay, well, then let's thank Andy once again for a great talk to end the conference.